Questions on the Chapter 7 homework? Huh? Number 3. Okay, so what was the question? So number 3, I probably don't want to go through that. That involves a lot of counting. So basically you're going to create your own bins and count how many is in each bin, and that's what you probably listed based on. The deviations is just the decimal point place, right? So you'll just look, so if you're looking for the deviations, then you're just, the numbers you're looking at is 0.0013, 0.0013, 0.0013, 0.0014, and etc. And basically you're going to try to draw a histogram where you're going to put things in certain bins. So it's going up to 24. It doesn't say how many bins you should use, but you can probably use 5 or so. So maybe something from like 0.0010 to 0.0015, and then you do 0.0015 to 0.0020 or 0.0020 to 0.0025. You know, that's just an example. And so basically you're going to count all these guys, right? So you know that for 0.0013 and 0.0014, you count those off 1, 2, 3, 4, 5, 6, 7, 8. Right, so that guy would give you 8 out of, how many are here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 50 data points here. So 8 out of 50, and so that one would be this, right? And then you continue, because it just asks you about creating a history. So you'll count the rest and you go off like that. In general, you won't be required to like count stuff. Like if in the questions where you use bins, they'll actually give you the bins. Sort of like in question 13. Question 13 is a good problem to know how to do. But yeah, so in general, this is one step behind where you will be required to start. Because this one requires that you're going to have to do the counting yourself. You won't always have to do that. I don't particularly want to dwell on that kind of problem because we're not really going to be doing it. Yes?
In 13, there's a section where it's asking for the quartiles based off the estimation.
So, problem 13. From the estimate the medians, the quartiles, and the mean variance. Okay, so let's actually do problem 13, the complete problem. How about that? That's actually a good idea. It's very possible for a problem like that to be on the final or definitely on the test. So let's actually do problem 13. So we're given these tables. We have the grades. (40 to 50, 50 to 60, 60 to 70, 70 to 80. 90 to 100. And we have the number of students, which is basically functions as a frequency. So we have 3 students, 8 students, 11 students, 4 students, 3 students, How many is that in total?
32.
There were 32.
Yeah.
Right, so you add these all up so you get the total. We're going to need that. Now it says construct, using the table, construct a labeled histogram. Now remember, usually labeled histograms, they go by relative frequency, so I'll probably compute that first. Right, so how do we find, so we're going to do part A ultimately, but first we will find the relative frequency. How do we find the relative frequency?
Number of students over 12.
Right, you take the number in each part divided by the total. So this is 3 over 32. This is 3 over 32. This is 8 over 32. This is 11 over 32. This is 4 over 32. This is 3 over 32. Did anyone compute the decimals for these?
0.09.
0.09.
0.25.
134. 0.13.
And this was 0.09. Did that add up to 100? It should be very close to 1 if it's not exactly 1. But it should be very, very close. And so those are our relative frequencies. So now we can do the histogram. The histogram doesn't really matter what your title is, just make sure it makes sense and has a title. Histogram for grade distribution. Very bad to have any kind of chart without saying what the chart is about. So remember, we plot the category versus relative frequency. So down here we'll have the grades, here we'll have the relative frequency of the grades. So our grades are just going to be the bins. So it's 40 to 50. And then we have 50 to 60. Then we have 60 to 70, 70 to 80, 80 to 90, and 90 to 100. And basically we're going to plot all these numbers. So we will have, the first one is going to be like 0.09. Then you will have 0.13. Then you will have 0.25. Then you'll have 0.34. So in the 40 to 50, we have the 0.09. And the same thing for the 50 to 60. So 40 to 50 and 50 to 60 are both levels here. The 8 will give us 0.25. So that should sort of line up with here. 70 to 80. So we have 40 to 50, 50 to 60. 0.25. 70 to 80 would give us the 0.34. So that one's going to be slightly higher. '80 to 90 would give us that 0.13. And 90 to 100 would give us back that 0.9. So that's basically what the histogram would look like. Any questions on that? So yeah, you just find the relative frequency. Those go on the vertical axis. You label it relative frequency. And then the categories go on this axis. So histogram, we don't put any spaces between the bars. And we order the numerical values in ascending order. Right? That's the standard form. Okay, so now in part B, we basically want to estimate the median, the quartiles, and the mean. So let's start with the median. So how did we say we do this?
12 divided by 2.
12 divided by 2, right? It's roughly halfway, so we need this, we need the position that it occurs in. This occurs in the 32 divided by 2th position, right? Which is basically just the 16th position. Right? So now we need to figure out a way to estimate what happens in the 16th position, right? So here we have 3. Move down here, we have 6. Right? Move down here, we have, right? You basically add the cumulative frequency until you want to get to 16. So here we have 6 plus 8, that gives us 14. So to get to 16, we need 2 into this bin, right? This is 2 steps into the 70 to 80 bin. So now we have to sort of figure out what is the step size, right? So we know how deep we have to go into this bin. How did we do that?
Right minus left and then over the frequency.
Right, so we have step size equals bin length. Right, so it's the right minus left over 11. So this was just 10 over 11, which is like 0.9. 0.99? 0.9090, right? So 0.91, so that's the step size. So basically what do we do? The median is going to be equal to the left endpoint of the bin plus we're going to take the number of steps we need times the step size. That tells you how far into the bin we want to go. Right? So we're going to start at, this means basically we start at 70 and we're going to add the number of steps. We need to take 2 steps and each step must be of size 0.91. Right? So the median should be roughly,
71.82.
it was what? 71.8. Right, so, you know, roughly 72-ish, 71, 72-ish. Right? Again, it's an estimate. You don't have to be exactly on the mark here. You just want to have a rough idea. The quartiles are actually very similar. You just need to remember that the first quartile is the median of everything below the median. So, and the third quartile is everything, the median above the median. So what happens is the median will happen halfway to the end. That means the first quartile will happen a quarter of the way, right? And then the third quartile will happen 3/4 of the way. So basically for Q1, so you just, let me just write this down so you sort of see what's happening. So basically when we think of the box plot, Q1 is the value here, the median is here, Q3 happens here. Now this takes up roughly 25% of the data, right? To get up to the median, it's 50% of the data, right? So this is like a quarter of your data, this is like a half of your data, right? To get up to Q3, you're gonna take 75% of your data, which is equivalent to 3/4. Right? So in each case, you just multiply how many terms you have by the respective fraction that you need. Right? So Q1 occurs in the 32/4 position. Right? 32/4 is what, 8? And then once you figure out the position, everything else now is just like the median. You're going to have to find the number of steps you need into which bin and what the step sizes are. Same deal. So we have to figure out, how do we get to the 8th position? Well, these 2 bins, the end of that gets us to the 6th position. This means we need 2 more. So we need 2 steps into this bin. This means I need 2 steps into the 60 to 70 bin. Let me continue this over here. I want to keep this table up. And so now what do we want to do? We want to figure out the step size. And again, it's bin length over frequency. So this guy is going to be 70 minus 60 divided by, there are 8 people here. So it's just 10 over 8, which is roughly what? 1.25 each step size. So this means Q1 is going to be equal to, again, you take a left endpoint plus number of steps times step size. So the left endpoint of this bin is 60 plus number of steps we need is 2 times the step size is 1.25. So this would give us what? 62.5. Right, so you can estimate roughly 63. Right, so if you're off by like one less, 62 or 64, I'd give it to you. It's not an exact science. It's an estimation, right? The key word here is estimate. Right? In general, you'll have thousands or millions of data points. Right? If you're off by 1 or 2, grand scheme of things, it won't really matter. Right? Yes?
To calculate the position, would it be, I did it a little differently as opposed to just doing it by 4. I took how many values were below the mean and divided that by 2. So that gives you like the 7th position. Would that be like wrong?
It's not wrong, but it's like...
Is that less accurate?
Huh?
Would that be less accurate?
It would sort of be more accurate. I mean, technically, if you wanted to be like super accurate, what you would do is the median would be the average of the 16th and the 17th position. So then you calculate the 16th and the 17th and then divide that by 2. It's just not necessary for our purposes. I mean, to just keep it simple, just assume it's a quarter of the way, a half of the way, 3/4 of the way. There's really no need for us to be any more accurate. This gives us a good enough estimation. Especially if there are a lot of numbers there, it's just extra work. It's not that it's wrong or anything, but you're giving yourself too much work in that case. Just keep it simple on yourself. I mean, the gain in accuracy you get by getting any more deeper is just not worth the half, basically, is what it boils down to, right? So we're just estimating here. So in the same way, so this guy here is our first quartile, and Q2 is pretty much similar, except now Q2 occurs in the, now we'll take 3/4 of the 32. Right. So 4 into 32 goes 8 times 3/8 is 24. So this is roughly the 24th position.
Is that Q3?
Is it Q3?
What?
Q3.
Q3.
Q3, yes. Q2 we already did. Q2 was the median. Q3 is, so it's the 24th position. And so then we figure out who's in the 24th position and what's in the step size. So this is how many steps to get to the 24th. So here we were at 14. Here we would be at what, 25? So we need one less here, right? So we need 10 steps into this thing. This means we need 10 steps into the 70 to 80th thing. Now I'm going to find the step size. It's the length of the bin divided by the frequency. We did this one before. This was a 0.91. This means Q3 is equal to the left endpoint plus number of steps. Size is 70 plus, now I have 10 times 0.91. So this is like 79.1, roughly 79. So this was Q1, that is Q3. We had before Q2 was roughly 72.
Do you need Q4 or no?
No, there is no Q4, right? There's the lowest Q1, Q2, Q3, and the highest, right? That's how we name them. What else do we, now we need the mean, and we only need an estimate for the mean. The mean is going to be approximately equal to this estimation. There are 32 total numbers. Right, so again, remember for the mean, we assume that we take on the average value in each interval. So we have 45 is the average here, and there are 3 of them. So we have 3 times 45 plus 3 times 55 plus 8 times 65 plus 11 times 75 plus 4 times 85 plus 3 times 95. And you compute that number. 70.9. So that would be our estimate for the mean, right? Just assume that you have this many numbers in each bin, and assume they all take on the average value. So on average, they take on this value, and then we just sum all those values. On the mean average. Right, so problem 13 is a really good problem. I mean, if you get a question from this chapter on the final, more than likely it will be something like this. They're going to ask you a histogram, and they're going to ask you to estimate all these things. They might also include estimating the standard deviation, which, again, you use this estimate for the mean, and just do that formula, and again, you take advantage of this. So I actually did an example when you did that in class last time. I'm just trying to think, is there anything else I want to say about this kind of question? It is also possible for them to not give you frequency and just give you the relative frequency. That's also a possible scenario, right? Where you're not given this, you're given that. In which case, to draw a histogram, it's easy, you just use the given numbers. But then, one way to deal with that situation is to figure out these numbers backwards. So basically, you multiply 32 by this to get that.
We're going to be given the total?
And you can use it. Huh?
We're given the total?
Yeah, they'd like give you the total in that case. Usually. I have to check if there's ever a case where they don't give you the total. And then I'll deal with that when it comes. I think in that situation they would give you the total, but if not, I'll check on it and we'll see. And I'll tell you how to deal with that case. Otherwise, I wouldn't worry about it. Someone asked about 15, the table below from Excel summarizes data on the university expenditures, blah, blah, blah. Let's do this. Yeah, 15 I'd probably skip. You could essentially do the whole thing in Excel, by the way. Just program these formulas into it, and it'll be done. You don't really need to know how to do something like that by hand. Any other questions?
19.
Huh?
19.
19. Okay, suppose you attain an average of 73 on 3 exams during the first half of a course. 5 exams are scheduled for the second half. What must your average be on the remaining 5 exams to finish with an average of 80 for the entire 8 exams? you know the average, and they're talking about the mean average here. Average of 73 for 3 exams. Average. We want to figure out what average do we need. Let's call it X for 5 exams, so that average of the 8 exams is 80. Right? So in other words, here, basically you need to find X. What's the average grade? Okay. Any ideas on how to attack that? Yeah.
So you multiply 8 by 80, and subtract 73 times 3 from that. And that would give you how much you need to have for total for the last 5 exams, right? And then you divide that by 5.
Right. So put that in other words, the idea is, again, sort of taking our cues from the estimation thing, pretty much assume that every grade is the average grade, right? So assume the first 3 grades were 75, 73. So basically what you want is, you have 3 times the 73, plus you're going to have 5 times whatever average grade here, divided by 8, which is what he said, should give you the average of 80. He said it in a different way. He said 80 times 8 should give you blah, blah, blah. But basically that's what he said. So this is going to be the average of your 8 exams. On the first 3, you average a 73. You want to know what is the average on the last 5 to get 80. And you basically solve this for X. So this is the average of 8 grades. Right, so the total grade over the number of grades. And so this would mean X would be 80 times 8 minus 3 times 73, then divide by 5, which is what Felix said.
Will you add
Right,
it
so-
to 80?
so-
84.
It's what?
84.2.
84.2. Average of 84.2. So the trick here was just to manipulate this formula by making assumptions like this, because numerically they all work out, right?
And
It
that's
could be
the
the same.
same as just like multiplying 7 by 3 dividing by 5 and adding it to 80.
And adding it to 80? No.
Yeah, because like 73, so to make that an 80, you need 7 more. 7 for the 3 tests would be 21. 21 divided by 5, 4.2 plus 80, 84.
Oh, well, yeah, you were computing like the excess that you need. Yeah, that's another way to look at it, I guess. To me, this would be the most straightforward way, but yeah, sure, that would also work. Other questions? Maybe one more? Number 5. It's a good one to end on. If anything, at the very least, it's a very instructive one, because some of the things I'm going to talk about in chapter 8, I'm going to be going back to this idea and then taking advantage of it. So let's finish off with chapter 5 and see how far we get into chapter 8. We don't really want to spend long on chapter 8, but it's sort of a lot of variety. So chapter 9 is the really important chapter for us, but chapter 8 has all the definitions that we need to use chapter 9. So you can think of chapter 8 as an introduction to chapter 9, so I'm going to want to go through that quickly. But let's finish this. So we have a data set here, and it is 3 minus 2, 7, 10, 5, and 3. And the 3 is not a typo, it literally occurs twice. Assume that there are 2 3s. So then A, we need the median, mean, standard deviation, and variance. That's part B. Okay, so let's do that. So how do we get to the median? The middle guy. How do we get to the middle guy? Is there anything we have to do first? You have to make sure they're in order before you can say who the median is. So arrange from lowest to highest. So we have minus 2, 3, 3, 5, 7, 10. So 1, there are 2 guys in the middle. So the median would be 3 plus 5 over 2, which is 4. Let's talk about the mean. How do you do that? Well, you add them all together and then divide by the number of numbers, which are 6. So we have minus 2 plus 3 plus 3 plus 5 plus 7 plus 10 all over 6. What was that? 4.33. Is that an estimation? You rounded? So the mean is roughly that. Let's do the standard deviation. So standard deviation, the formula is the square root of each value minus the mean. You square it, you add them all together, and divide by n minus 1. We think of this as a sample. So we have minus 2 minus 4.33 squared plus 3 occurs twice, so I can double this. 3 minus 4.33 squared plus 5 minus 4.33 squared plus 7 minus 4.33 squared plus 10 minus 4.33 squared. All of that over 5. And what was that roughly? 4.08. And finally, the variance. How do you get the variance? Right, you square the standard deviation, which is just 4.08 squared, which is 16.7. 75, someone said?
65. 65 should 7.
Oh, 65, which rounds the points down. Okay. So those parts were just applying the formula. That wasn't, that part wasn't supposed to be hard. Now, they ask you in part B, suppose 15 is added to each of the data values. What are the new values for the median, the mean, the standard deviation, and the variance? And you can do this without repeating all the details of the calculation. So they expect you to see a shortcut here to get to the answer. So redo A with 15 added to each value. So now what's going to happen? So now I'm looking at the numbers 2 plus 15, 3 plus 15, 3 plus 15, 5 plus 15, 7 plus 15, 10 plus 15. Now they're in order and I'm adding a positive number, so they remain in order. So the median would be, again, just the average of the two middle ones. Right? So you have 3 plus 15 plus 5 plus 15 all over 2. The thing is, this is 3 plus 5 over 2 plus 15 plus 15 over 2. And so here this gives you the old one, which was 4. This gives you 15. So it's 19. Right? And basically what you're supposed to take from this is if a constant is added to each value, the new median is equal to the old median plus the constant. Let me name this constant. If a constant k is added to each value, the new median would be the old median plus k. Right? That's sort of the shortcut that they wanted me to figure out by doing this. Right? It ends up being the old median, you just add to it whatever guy you added to everyone else. Right? That actually just makes sense. Right? Because each value increases by 15, you pick the middle one, he's going to increase by 15. Right? So the median should increase by 15. Now the next thing was the mean. The idea is, how would the mean actually change? Well, you sort of do this idea again. You have minus 2 plus 15. You add that to 3 plus 15. 3 plus 15. 5 plus 15. 7 plus 15. 10 plus 15. All over, there are still 6 values. Now the idea is, what you can do is, you can take out 6 15s plus, maybe the minus 2 plus 3 plus 3 plus 5 plus 7 plus 10 all over 6. So you want to be able to do this with the minimum calculations possible. So what you'd realize is that this guy here is just the old mean, right? All the 15s that you added, you can isolate them in a term on their own. There are 6 of them, right? So they contribute this part, which is just 15 plus, what was the old mean we had was 4.33. So the new mean is 19.33. And again, there should be a takeaway from this. If a constant k is added to each value, the new mean is equal to the old mean plus k. The idea is we want to figure out how do things change when we add a value to everything, right? So the median changes by adding the new value. Let me emphasize here, this is the new median. And the mean changes in the same way, right? If you add a value to everything, you should add that value to the mean, and that'll be the new mean for the whole thing, right? So you don't have to redo all your computations, just add whatever value it was to the old computation. How does the standard deviation change? Before we actually do it, how do you think it will change? It won't change, right? Because what was standard deviation? How things are spread out. If you add a value to all the values, they all just shift over. They'll still stay spread out the same. So we expect the standard deviation to give us exactly the same number. Does that actually coincide with what the calculations would look like? Well, let's see. So remember, we're looking at the new value, so this is minus 2 plus 15 is the value, and we're subtracting the mean. But the new mean was actually 15 plus 4.33. Right? So this is the new value, this is the new mean. And we're going to be doing this repeatedly. So this is going to be 3 plus 15 minus 4.33 plus 15 plus now what you're realizing is this 15 that you added gets subtracted again. Right? So basically what you're going to get was the old one, minus 2 plus 4.33. Minus 2 minus 4.33 squared, plus 3 minus 4.33 squared, plus 5 minus 4.33 squared, all over 5. So basically, because you add 15 to each data point, you add 15 to the mean as well, so that excess that you added gets subtracted, you get the original back. So we had that, this was, I forgot the number, this was 4.65? 0.8. Who was 4.65? Oh, the other guy. So what you should take away from this is if a constant, I don't think we're going to get to talk about chapter 8 much. Maybe I'll just introduce it. If a constant is added to each value, then the new standard deviation is just the same as the old standard deviation. Right? So don't waste your time computing it again. Right? It'll stay the same, because it just means everyone gets shifted, but they all maintain the same space between each other that they had before. This idea is going to be important to us when we're studying trends and we want to figure out, oh, what if this happened? So how does the trend change, right? That's going to be in chapters 8 and 9. Of course, this also implies that variance will be the same as well. Because the variance is just the square of the standard deviation. Standard deviation doesn't change, so the variance won't change either. Let's see. So now we sort of, oh, by the way, I'm sort of doing part D as we go along, right? So in part D, when they're talking about state the general rules based on your observations, these are the general rules, right? So I'm sort of doing part D as we go along, right? This is what they expect you to be able to tell me. So C, each value is multiplied by -5. How do the new values change? So what do you think for the median?
Multiply that, divide by.
Right, so it's just going to be, the values are now 2 times minus 5, comma, 3 times minus 5, comma, 3 times minus 5, comma, 5 times minus 5, comma. The next number was 7 times minus 5, comma, 10 times minus 5. So the median is, now basically what the negative, multiply by negative do, it will just make this one the smallest one. But remember, ascending or descending order doesn't matter, it actually gives us the same thing. So again, the median is the average of these two. So it's minus 5 plus 5 times minus 5 all over 2. Which now minus 5 is a constant factor. I can factor that out. This is 3 plus 5 over 2. So this is minus 5 times 4. So it's minus 20. So what's the general rule here?
Multiply.
Right. If all values are multiplied by a constant k, then the new median just equals k times the old median. What's the next one? The mean. Same sort of idea. So we would have to add all these guys. 2 times minus 5 plus 3 times minus 5 plus 3 times minus 5 plus 5 times minus 5 plus 7 times minus 5 plus 10 times minus 5 all over 6. What happens here is there's a minus 5 in everybody, which means I can factor out minus 5. And I have minus 2 plus 3 plus 3 plus 5 plus 7 plus 10. So this is just minus 5 times 4.33. So that's what?
21.67.
Minus 21.67. Okay, so general rule here. You multiply the mean as well by the constant. General rule. So we did the median, the mean, standard deviation. Which we called S. Let's sort of write out the first few terms to figure out how things will change. So here we have over 5. So what's going to happen here? Well, the first value was multiplied by minus 5, but now we minus the mean, which is multiplied by minus 5. Similarly, the next value multiplied by minus 5 minus the mean multiplied by minus 5 plus dot, dot, dot. Okay, what pattern do you see?
You just multiply.
-5 is a common term. I can factor him out. But be careful because there's a square here. So when you factor him out, he'll take on the square, right? Because power is distributed across products. So basically what's going to happen is you're going to have this -5 squared factored out of all the terms. So let's see how this would be. So now I can literally factor that -5 outside all the terms. Right? So this is -5 squared times don't worry, you'll never have to do this again. Once you do this once, you get the general rule, and then you apply it all the time. I'm not going to ask you to derive this. You should just know this from now on. So this means I can now take this guy and factor him off the radical, right? So S is now -5 squared times what's this number? It's just 5 times the old standard deviation, right? Which was 4.08. So that's roughly what? 20.4. Okay. Can you tell me a general rule?
We multiply by the absolute value of the constant.
Right, so notice here we multiply by -5, but the standard deviation got multiplied by a +5. And that's because you squared it and took a radical. That gives you the absolute value of a number. So if all values are multiplied by k, then the new standard deviation is equal to absolute value k times the old standard deviation. So multiplication actually changes your spread. It changes it by a constant factor. There's going to be a case where we're not going to want this to happen, and so we're going to try to fix that happening, the scaling idea, in chapter 8. So ultimately, knowing this is going to indicate there's going to be a problem later on, and we're going to have to try to fix it. So just so you see that. And of course, how would the variance change? This implies, well, the variance in this case will just be the square root of the standard deviation. Right? Which, remember, this standard deviation ends up being your absolute value k times the old standard deviation. So this just ends up with the radical absolute value k times the old variance, which in this case would be radical 5 times, the other one was 0.465, was it?
4.0. Oh, sorry, 16.6.
16.6. And that's going to be roughly what?
Should it be 5 squared, not square root of 5?
Yeah,
5
square.
squared.
Square was
I
the
thought you just.
Right, so it'll be this squared, which if it's an absolute values, it won't matter, right? So it's just 5.
Don't you multiply by the square root of 5? I mean, 5 squared.
Yeah, so
Yeah, but if this is 5 squared and then I take the square root of it. What?
Should end the 5 squared.
Because if you
Isn't there any
if you square 20.4,
Yeah, 20.4
you
square.
get like 400 something, right? So it should be it should be the whatever the constant is squared times the old variance.
Let's see, where do we get up? So here, okay, here, we had 5 times that. Right, so the variance would be the square root of this, no?
The square of the standard
20.4
deviation.
Oh, right, yes. Why was I taking the square root? I'm still stuck in standard deviation mode. Yeah, we should be taking the squares. What the hell? It's the other way around. Right, you want to get rid of the radical. Okay, so this one was this, so we're squaring. So this is squared times the variance. So this is squared. So this is ultimately what?
416.2.
416.2. So the rule here is, well, I sort of wrote down the rule here. New variance. And you don't have to put absolute values here because it won't make a difference because you're squaring, you're getting the positive answer anyway. We'll end there. We'll do chapter 8 next time. Pass up your homework.